Now, if we look at our example from the last video, we will notice a problem though. And that is that when you look closely, then the vector that is defined here towards this new position we defined is shorter than the ones that are further away. Because of course, when we look at our graphic again, then of course it makes a difference where our point in space is. A point that is closer to the first point, of course, will be shorter. Makes sense. Now this is actually a common problem because sometimes I want the directions to be equal in length. And this is actually where normalization comes into place. Because to normalize something means I put it to an exact length of 1. And this is very important, not only because it's very handy to then work with this, because, if something is exactly 1, I can multiply it with any number and then get a expected result. It's very easy just mathematically to work with something that has a length of 1. But also it's important later on for any kind of mathematical function like cross product or dot product or other things. They all expect to have normalized vectors as inputs, otherwise they will give us wrong results. And we already know this concept, for example, from a ramp parameter. It also expects an input between 0 and 1. So as you can see, not only vectors can be normalized and then they have a length of 1, float attributes or any kind of data really can also be normalized, which means it's between 0 and 1. And this is actually the reason a normal is called a normal, because it has exactly a length of 1. If you want, you can check that. So normalization is very important, and to do that, there's actually a very handy function called, surprise, normalize. So to make sure that all the vectors that we calculated here have all the same length, we just normalize them. So we can do this in the next line. We don't have to put it into the same line, even though we could, but it's a bit harder to read it that way. So let's put it in a new line, and all we do is we normalize with a normalize command or function, and we put in what we want to normalize, which is the vector that is always saved in n, and the result of that will go into n. Let's press Ctrl Enter, and you can see they now all have the same length of exactly 1. Now you might say, wait a minute, those vectors don't look like the length of 1. That doesn't make sense. It would be that length, right? Well, this is obviously just a visualization. If you look down here, you can kind of guess that this actually has the length of 1. You can also change the visualization with D, and then under guides, I think it was, there is the scale normal, and surprise, it's set to something lower than 1. So let's set it to 1. And you can see now, if we find one, maybe this one, this is actually pretty much exactly 1 meter in Houdini scale. So let's turn this back because nobody wants to work with such long visualizations. But to make sure, let's quickly calculate the magnitude of a vector, and we can use the length command for that. So let's quickly calculate it and save it in our own attribute, and surprise, it's exactly 1 after we normalized it. Let's quickly comment out our normalization to see what we had before. And here you can see that the length before was kind of all over the place because, of course, every point had a different distance to our defined position. And again, one of the reasons why this is cool is that I can now take the normal and multiply it with any number I want, for example, 3.5, whatever, and then each vector will have exactly that length. So of course, anything I multiply with 1 will result in the number, and this is really, really handy to work with. So just keep that in mind, because this is one of the many reasons why normalization is so helpful. And there's actually one neat little trick here that you can use normalization for. It's not really that useful, but it's a fun little trick to think about. If I want to turn any kind of object into a sphere, I can do that with the normalization of its position. What that means is, since the position defines basically, as we've seen, also the distance to the center, by normalizing it or turning its distance to the center to exactly 1, I can turn anything into a sphere because I make sure that every point, no matter what, will always have a distance of exactly 1 to the center based on its current position. And this allows me to turn anything into a sphere. Are there many use cases for this? No, but it's a fun little thing to think about. Okay, so keep that in mind. Normalization is a very important technique and we will use that quite a lot from now on. So thanks very much and see you later. Cheers.